Today we're going to continue on in the note packet, and we'll do a little more than what we did yesterday. We're going to talk about states of matter. And we're going to talk about some other forces involved with some things here. So let's, again, this should be, some of this stuff here should be junior high stuff or stuff that you learned when you're in 5th grade or even sooner. The states of matter, again, anything and everything can exist as either a solid, gas, or a liquid. Okay? Even you. The good news is we're in this gelatinous form that we're in right now, and I want to stay in this form as long as I can. However, if I'm exposed to a lot of heat, I may vaporize. Or if I'm exposed, or I'm sorry, if I am in the presence of a lack of heat or a lot of lack of heat, I may freeze into a human popsicle. So, and again, some people might think, all right, if I look at hydrogen gas, okay, that's the way that it exists at room temperature. So oftentimes when we refer to things, we're talking about the normal temperature or at what we encounter each and every day. So water, obviously we know water can freeze, it can turn into a solid, and it can turn into a gas. Okay? We see that all the time. That we can witness, those 3 phases. But oftentimes we can't witness that with everything else. Some other terminology, when a liquid changes to a solid, that's considered freezing. And think about this. Whenever you hear the term freezing, what's the first thing that pops into your mind? Cold.
Ice.
Okay, ice. In other words, when people generally think about freezing, they think about something that has a lack of energy or is cold. However, when you go and fry your eggs in the morning or whenever you do it, you're doing it on a frozen skillet. In other words, freezing is a scientific term that means it went from a liquid to a solid. So if I touch that frying pan after it's been on the stove for a while, that frying pan's still frozen, except I'm going to get burnt quite badly. All right? So freezing doesn't mean cold. That's just the way that we've been conditioned all along, that when we go outside, ooh, we're freezing. Well, hopefully you're not freezing, because that would be a mess. All right? Boiling, okay, you can think in terms of boiling as being warm. Again, that's the way we're conditioned. However, you have to realize that the air that we're breathing has already gone through the boiling phase. So we're inhaling gases that have already gone from a liquid to a gas. All right. So part of this class also will help you understand that some of the layman's terms that's thrown around, freezing, boiling, cold, hot, doesn't necessarily apply. It just is a phase change. All right. And we'll actually have a lab that will undergo a phase change on Friday for you guys. Okay. A mess? Oh. All right. Phase changes again. If we undergo a phase change, that means that we have a solid that can change into a liquid that can change into a gas. All right. Now, is it possible for that liquid to skip is it possible for that solid to skip the liquid phase and go straight to a gas? Yeah, that's called sublimation. All right, stop. You're done. That's brutal. Yes, it is possible for it to skip a phase. All right, and we'll talk about that a little bit later on today. So not all things have to undergo that series of change. But anytime that we take something and change it from a solid to a liquid to a gas or any of those combinations, that is a physical change. Which means that if I start with liquid water and I change it into solid water, is it still water? Yeah. Has it undergone a chemical change? No. We'll talk about why that changes here in a second. Kinetic molecular theory. In other words, whenever you hear the term kinetic, what do you think?
Friction.
Okay, no.
Energy. Moving.
Moving, there we go. So kinetic deals with motion. Okay. So when you hear about kinetic energy, we're talking about the energy of motion. All right. So when we talk about kinetic energy, we want to talk about how quickly the molecules or particles are moving. So if we look at a gas, are they moving quickly or slowly?
Quick.
Very quick. All right. Gases have the quickest kinetic energy. In other words, they're so fast that the bond that's between the other molecules is very weak because it's too strong. It just leaves. However, if you look at a solid, okay, those molecules or particles are very, very close together, and they have very little kinetic energy. All right, so, and we're going to talk about the forces between molecules or atoms today. Okay. Intermolecular forces. Okay. We've already talked about intramolecular forces. Intra means between atoms. We talked about polar covalent, non-polar covalent, and ionic bonds. All right. So those are the forces that are between atoms. The types of forces that we're going to talk about today are between molecules. All right. So we're not going to talk about any of the forces between atoms today. Okay. When we talk about intermolecular forces, we're going to talk about the relative strength of these forces. Who do you think has a stronger force, gases or solids? Solids. We just said it a second ago. So the reason why things are solid is because the forces that are holding those particles together are very, very strong. So it makes it difficult for those solids to move apart. How do you think I could weaken the intermolecular forces?
Out of gas.
Well, I've got a lot of gas here. I heard somebody back here.
Go through a thing.
No, there was a male voice.
Oil of mine. It was heated up.
Heat it up. Give it some energy. In other words, as you heat something up, what happens to the particles?
They get mad.
They start moving a little more. They don't get mad. They start moving. Hopefully the particles don't have emotions. That would be
Yeah,
brutal.
they do, because you said they got excited.
Excited's different. So as we warm something up, the particles begin to move. And as they go from a solid phase to a liquid phase, they're getting more and more motion, which kind of weakens the forces in between. And as we actually go from a solid to a liquid phase, now those particles are starting to move around a little more freely, but it's not moving as freely where it can change into a gas. Okay? So once you've given it enough energy and it's broken that intermolecular force, now we have a gas. Actually, that's my lead into effective temperature. Okay? So the average kinetic energy, and this is funny, because I do this on every test, even in AP. When you hear me say average kinetic energy, automatically think temperature. Okay? So actually a redundant statement. Average kinetic energy refers to temperature. So if I take the average kinetic energy of the gases in this room, I'm taking the temperature of that. All right? And so I may say, all right, average kinetic energy, and then equals or means what? And then I'll give you some options. Always pick temperature. Okay? Condensation. That's when we actually go from a gas to a liquid. When it rains outside, we're undergoing condensation. Okay? In other words, the clouds in the sky, you've all been told this, that's all water vapor, right? And sometimes there's some ice crystals up there that's undergoing movement from the wind. Okay. But when that gas changes into a liquid, do you think the atmosphere can hold that liquid up? No, that's when it rains.
Kind of like when you defrost your car. I don't know.
Then the solid goes to a liquid. Yeah, I like that. Or say that it's very cold outside and you've been running, and then you jump in the car with the windows up. What happens to the car? Inside.
It gets
Foggy. Oh yeah, that's one reason why if I go out on a run, I make sure that my windows go down after I get in the car, or else I can't see.
Yeah,
Yeah, but you're giving off a lot of heat and water vapor from the sweat. Yummy. All right, effective pressure.
problem solved.
Yeah, you'll cool down.
No, just problem solved, don't be a runner.
Oh Lord,
True.
that's the best thing to do.
Running's
All right, effective pressure. We're going to talk more about pressure when we do gases, not so much this topic. So go ahead and just write that. Or is there anything for you to write down about that?
Yeah. No.
Okay. When you hear me talk about 1 atmosphere, and this is just a little foreshadowing for what we're going to do next semester, 1 atmosphere is what we're experiencing right now. It's the atmospheric pressure that we're feeling. If this atmospheric pressure weren't here, we'd be in bad shape. We wouldn't be here. So think your atmosphere. But again, the stronger the intermolecular forces, the stronger the bond. Okay. So is it possible for me to take a gas and pressure, and we haven't talked about it yet, so I'm relying on your past experience. Can I take a gas and push it together?
Yeah.
Oh yeah.
Yes.
In other words, I can push it together so much that it actually changes from a gas to a liquid. So if you ever go into Kroger or Walmart or whatever place that sells helium balloons, there's a big tank. You go and take that tank, it's filled with helium. Put it to a more practical application. The tanks for your grill outside, if you ever pick those things up, they're heavy. Pick it up and kind of shake it around, you'll feel a liquid in there. Well, it's only a liquid until we open up the valve and allow that liquid to change into a gas. Okay, so we can pressurize gases into a liquid, and then when we expose it to a lower pressure outside, it'll change back into a gas. However, what you cannot do is you can't squeeze liquid particles so close together that they turn into a solid. That won't. The three types of intermolecular forces that we need to know. And again, these are between molecules. Okay? And if you want to write that between molecules right here, that's a good idea. Okay?
What is?
The intermolecular. Okay? And it even says the three types which hold molecules together. And these are in the order from weak to strongest. Okay? So dispersion forces, here we go again. Dipole, 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 dipole.
Dipole.
And then hydrogen bonding. Okay? And we're going to go over each one of these respectively. Okay?
How much more are we doing?
To the twos.
Oh, okay.
Now, there are no ones. Don't ask me why. Well, actually, I know why.
You
I
also
took them
missed
out.
Page 19.
19?
Yeah, we
Very
have no
nice.
pictures.
All right. But there's a lot of pictures in there. All right, let's talk about the first intermolecular force, which is the weakest of them all. It's called dispersion forces. All right. Now, whenever we want to determine what type of intermolecular force we have, we need to draw a Lewis structure. Okay, I know. You all love drawing Lewis structures.
Oh my gosh.
So once you draw your Lewis structure and you determine, hey, this thing is a non-polar molecule, not the type of bond that's between the atoms, but a non-polar molecule, then we only have one choice. We have very weak dispersion forces. Okay? In other words, if I look at this hydrogen atom, or I'm sorry, molecule, who has the greater attraction for this shared electrons? Neither.
Right.
Neither. Okay, hold on. Don't look at those yet.
There's only one circle.
I know. Okay.
That's the throw you want.
But what I'm asking is, who has the greater attraction for those shared electrons? Neither, because they're both hydrogen. They both have a electronegative value 2.1. However, the reality is, those hydrogens are trying to get those electrons. Okay? And if I were to take a snapshot in time of this molecule, if I took a snapshot in time, which of these two hydrogens has those electrons closer?
On the right.
On the left side here. The one on the right here?
Yeah.
How do you know that?
Because there's a D negative on that.
Partial negative charge. Okay? But as soon as I take that picture, what's going to happen is that hydrogen is going to pull and change it over to where it now has it. Okay? So this is called a momentary dipole. And I think I have it somewhere. Yeah, momentary dipole means that for a moment in time, even quicker than that, the electrons are closer to that hydrogen than that hydrogen. So it has a partial negative charge for a moment, and then it's a partial positive. So it keeps flipping back and forth. Okay? However, the easiest way to do this, look at the molecule. That's a nonpolar molecule. So the only type of forces that we're going to have in between these two molecules is dispersion. Okay? So again, dispersion forces are the only intermolecular force acting between nonpolar molecules. So you go and draw the Lewis structure and you go, oh, that thing's nonpolar. Boom, no question. Okay? All right. We'll come back to this in a moment. Highlight this or star this last statement here. In noble gases, or for noble gases, dispersion forces are the only forces acting between the atoms. Okay? Now, rarely do noble gases create compounds. However, there are a few with radon and xenon. But when we talk about helium, in other words, how in the world, when we look at that helium tank and it's filled with liquid, that means that the forces are so strong that we actually have it as a liquid phase. Okay? So, again, dispersion forces. And again, what causes that helium to change from a gas to a liquid? The pressure. Good. So we forced them together. We pushed them together so close that they actually change into a liquid. All right, dipole-dipole forces. Okay. This is the one of two forces that you could have for a polar molecule. Okay. So when you draw your Lewis structure and you get a polar molecule, this is one of the two forces that you could have. And again, these are between molecules. So dipole-dipole deals with a permanent dipole moment, or partial charge. So when you go and draw these out, you're going to notice that, ooh, that atom has a greater attraction for the shared electrons than the other one. Okay. So like if I look at, say, nitrogen gas here, it's a nonpolar molecule. They have relatively same molar masses as compared to carbon monoxide. However, the boiling point reflects the strength of the intermolecular force. The stronger the intermolecular force, the higher the boiling point. In other words, the more energy it's going to take to make it go from a liquid to a gas. Now again, it's not significant, but it is higher. All right. And again, dipole-dipole interactions are only about 1/100th as strong as an ionic or covalent bond. What that means is intermolecular forces are not as strong as the forces between atoms. And think about this. If I have water molecules, say I'm boiling water at home. When I boil the water, do the water molecules break apart into hydrogen and oxygen gas? Now, I want you to visualize this. Do the water molecules break apart into hydrogen and oxygen gas when it boils?
Yes.
Oh God, no. Think about this. If you expose hydrogen gas to a flame, what happens?
Fire.
Blows up, or fire. What happens when you expose oxygen gas to a fire? Does the same thing, but not as dramatic as hydrogen. Okay? So the only way that keeps that from blowing up is when the water actually boils in the liquid phase, it changes from a liquid to a gas. So in the air, we have H2O particles floating around. We don't have hydrogen and oxygen. Okay, that would be very dramatic if that happened. All right, hydrogen bonding. Okay, hydrogen bonding is our second type of bond or intermolecular force that takes place within a polar molecule. The exception here is you have to have hydrogen, and it has to be touching within the molecule nitrogen, oxygen, or fluorine. NOF. Okay? So nitrogen, oxygen, or fluorine. So nitrogen, oxygen, fluorine, and it's right there on the top of your periodic table. And just remember NOF, NOF. Okay, so hydrogen bonding only takes place, A, with a polar molecule, B, when hydrogen is connected to a nitrogen, oxygen, or a fluorine atom. Now, hydrogen bonding does not take place between atoms. It takes place between molecules. That's why I put this on here. So the type of bond between atoms is some type of covalent bond. Okay? Make sure you know the difference. Which of these two bonds is stronger, the covalent or the hydrogen? The covalent. Again, you can't heat this up and break bonds between atoms. You can heat this up and break bonds between molecules. It's going to take a significant amount of heat and effort to break the bond between these guys. These are very, very strong. These are very, very weak. That's why we can go from a liquid to a solid to a gas phase. Okay. All right, there's your homework. Actually, let's take a look at 2D. Let's do 2D real quick. Yeah? Or do you want to do it on your own? You can do it on your own if you want.
Wait, we're doing it together?
It's your call. Do you want to do it by yourself or together? 2D? Is it 2D? What does it say? It wants you to determine the intermolecular force. Read the question. 2D, the last one.
And air samples of each of the following indicate the kinds of
Intermolecular, very good. All right, so.
forces that can occur.
All right. So the first one, neon. Thank you. We're good. Neon. Again, what you must do is draw the Lewis structure. You must draw the Lewis structure to answer these. So with neon, I have 8. Okay. What type of intermolecular force do I have between neon, which is a noble gas? I had you starred or highlighted.
Dispersion.
Who? Dispersion. Good.
What did I say?
I don't know what you said. So dispersion forces. Okay? And again, in the notes it says that dispersion forces are the only forces acting between noble gases. Okay. All right, the next one, I2. So I2, let's find out how many electrons. So each iodine brings how many? 7 electrons. We have 2 of those, so a total of 14. Okay. So the iodine, again, make one of them your external atom. Give it its 8. How many do I have so far? 8. And then put whatever's left on the other atom. How many do I have now? 14. Is this a polar or a non-polar molecule? Why is it non-polar?
Because it has lone pairs.
No.
No.
What's that? Yeah, in other words, if I take the difference in electronegativities, okay, we have a non-polar covalent bond between here. Also, who has a greater attraction for these shared electrons? Neither. So there is no tug of war. And all the external atoms are the same. So this is a non-polar compound, okay, which means it has what type of intermolecular forces? Dispersion. Again, dispersion equals non-polar compound. Okay. All right, the next one, ammonia. NH3. Okay. So nitrogen brings how many electrons? 5, very good. Hydrogen brings 1, good. For a total of 8. Okay. And give the hydrogens what they want. So I have how many electrons? Is that polar or non-polar?
It's polar, but
It's a polar compound, very good. So we have a polar compound. And go on. What was that?
It's a hydrogen bond.
So it's not dipole-dipole?
No.
Why?
Because it's in the not thing.
Good. So we have hydrogen and it's attached to a nitrogen, oxygen, or fluorine. So this would be a hydrogen bond. Okay. And again, where does the hydrogen bond occur? Between here? Between the atoms? Yes? No? No. If I had another ammonia, it would take place in between. Pretend my hand's another ammonia. It would take place right between here. Okay. Make sure you know intermolecular versus intramolecular. All right. CO2. Okay. So carbon has 4 electrons, and each oxygen 6, for a total of how many? 16. So we have our oxygens, carbon, oxygen. And you guys have drawn this a couple hundred times, so you should know. Is that a polar or non-polar compound? Non-polar compound? So what type of intermolecular forces? Dispersion. There's only one choice. Okay. If it's a non-polar compound, there's no other choice. Okay. All right, CH4. So carbon brings 4, each hydrogen brings 1, total of 8 electrons. So polar or non-polar?
Polar.
Non-polar. Non-polar compound. All the external atoms are the same. No lone pairs on the central atom. So what type of intermolecular force? Dispersion. Good. All right. And the last one, and I might give you another one here. CH3OH. This actually looks like this. Okay, we haven't talked about any organic stuff yet. Okay. That's what your molecule looks like. Is that polar or non-polar? I don't know if we've talked about something like this yet. Is that polar or non-polar? Definitely what? Definitely polar. I like that. And again, think about this. If this carbon's your central atom, are all the external atoms the same? On the carbon? Nope. Okay, so we have this leg, so to speak. So we know it's a polar compound. So now we're down to dipole-dipole or hydrogen bonding. So what type of intermolecular force do we have? Dipole?
There's an oxygen.
Oh, there's an oxygen. So we have a NOF situation.
Oh.
So you have a polar compound and you have a hydrogen attached to it. So hydrogen bonding. So if I had more of these around it, they would have hydrogen bonding connecting them. Okay? Yeah.
When we figure out if it's polar or non-polar, do we do the thing that we learned last time?
Yes, everything that we've learned, we still apply.
But we don't use, like, we don't have to subtract it, we just use the rules from the...
Correct. So once you have it drawn, we're not worrying about the forces in between. We're looking at whether it's a polar or non-polar compound. Not if it's a non-polar covalent bond or a polar covalent bond. Because a lot of these, even though this is a non-polar compound, all the bonds in between are polar covalent bonds. Okay. All right. So go ahead and work on the homework.